You can't see it, and you can't feel it. At least, not at first. But right now, there is a silent metabolic shift affecting over 1 in 3 adults. It is the common denominator behind fatty liver, type 2 diabetes, PCOS, and even heart disease. We call it insulin resistance. Most people think it's just about eating too much sugar, but it's actually far more fascinating and dangerous than that. It is a brilliant evolutionary survival mechanism that kept our ancestors alive for millions of years. But in the 21st century, that same mechanism is backfiring. Today, we're going to look under the hood of your metabolism. We'll explore the evolutionary glitch that's causing insulin resistance, and we'll talk more about how you can flip that switch back. To understand insulin resistance, we first have to understand how insulin normally works. Think of every cell in your body like a high-security building. It needs fuel, or glucose, in order to run. But glucose can't just walk in. It needs an escort. That escort is insulin. Insulin is a storage hormone produced by your pancreas. In a healthy body, it works like a perfect lock-and key. Insulin turns the key, the cell door opens, glucose enters, and your energy stays stable. When you eat, especially carbohydrates, insulin rises. Its job is to move energy out of the bloodstream and into tissues and cells, for example, within the muscle, liver, and fat cells. This keeps your blood glucose level in a safe range. When insulin is working well, muscles readily take up glucose, the liver stores excess energy, and blood sugar returns to baseline efficiently. This is insulin sensitivity. Insulin resistance happens when tissues stop responding normally to insulin's signal. But why does this happen? It's not because insulin disappeared. It's because the body is becoming resistant to insulin after a period of prolonged and excessive exposure to it. You are essentially marinating in a growth hormone that in high amounts tells your body to store fat and never stop. Insulin resistance is the presence of too much insulin for too long relative to what tissues can handle. Think of insulin as a knock at the door. At first, the door opens easily, but if the knocking is constant, day after day, hour after hour, you start to ignore it. This isn't random failure. It's a protective response, a way to prevent tissues from being overfilled with glucose. When muscle and liver are already saturated, meaning they've taken up all of the energy that they can, they become less responsive by design. This brings us to a critical question. Why is our body so good at becoming insulin resistant? If it's so bad for us, why didn't evolution weed it out? The answer lies in our history. From an evolutionary perspective, insulin resistance made sense. As I mentioned in the Fatty Liver Part 1 video, for most of human history, food was not a guarantee. Our ancestors lived through a cycle of feast and famine. When they found a berry bush or a honey cache, they needed to store that energy as body fat quickly in order to survive the coming winter or the next failed hunt. In this context, insulin helped us to store energy quickly, preserve fuel for periods of scarcity, and protect the brain as well as other vital organs during periods of fasting. During periods of illness, stress, infection, or seasonal food abundance, a temporary state of insulin resistance was actually advantageous. This is because it directed energy away from muscle and toward fat storage, and helped to preserve glucose for vital organs. In short, insulin resistance was a feature, not a bug. We are the descendants of the survivors who were the best at storing fat. We carry thrifty genes that contribute to the concept of thrifty metabolism mentioned in the Fatty Liver Part 1 video. The problem is that we now live in a world where, for many, the feast never ends. For many, there is no longer a demand to survive harsh winters outside. For many, there is no famine. We are using a biological software program designed for the Stone Age to navigate a world of ultra-processed carbohydrates and 24/7 snacking. Our survival switch is stuck in the on position. The body never gets a break from insulin signaling, so the adaptive response becomes chronic. What was once temporary becomes persistent. What was once protective becomes harmful. This is when insulin resistance starts driving other issues like elevated triglycerides, fatty liver or MASLD, rising fasting insulin levels, impaired glucose tolerance, and eventually type 2 diabetes. Insulin resistance isn't a cliff you fall off of. It's a long, slow slide. As we discussed in our fatty liver series, the liver is the first line of defense. Once the liver is full and becomes resistant, the fat starts spilling over into the pancreas. When the beta cells in your pancreas, those are the cells that make insulin, when those cells finally get exhausted and start to die off, that is when your blood sugar starts to spike uncontrollably. That eventually leads to the clinical diagnosis of type 2 diabetes, which we will discuss further in the next video. But remember, insulin resistance usually develops many years before your blood sugar ever turns abnormal on a standard lab test. And this is one of the most confusing parts for many people, because your blood glucose levels can remain normal for years while you have insulin resistance. This is because, for a period of time, your pancreas compensates by making more insulin in order to overcome that insulin resistance. So, glucose looks fine while your insulin levels are slowly and quietly climbing in the background. But after so many years of working overtime, your pancreas starts to have difficulty keeping up and insulin production starts to go down. By the time glucose levels rise, the system has usually been stressed for years. The good news? Our biology is adaptable. Because insulin resistance is a response to a stimulus, we can change that stimulus. The first priority is lowering the noise, or that chronic insulin signal. This usually involves sustainable calorie control, increasing energy use through movement, improving sleep because chronic sleep deprivation can contribute to insulin resistance, managing stress because chronic stress can also contribute to insulin resistance, and fasting overnight to allow insulin levels to fall. Over time, these strategies help to reduce insulin spikes. Things like intermittent fasting, reducing refined carbohydrates, increasing protein and fiber intake, these aren't just diets or trends. They are tools to let your cells lower that noise or insulin signal over time. Many of these are discussed further in Fatty Liver Part 2, and are also very much relevant for reducing and reversing insulin resistance as well. And if you haven't watched Fatty Liver Part 2 yet, you can find it on the Science MD channel on YouTube. The second priority is to build muscle. Skeletal muscle is your largest glucose sink. The more muscle you have, the more places your body has to put glucose without needing massive amounts of insulin. This is one of the reasons why regular weight or resistance training exercises are key. Movement in general also increases energy use, leaving less to be stored as fat. The third priority is protecting the liver. And again, if you haven't checked out Fatty Liver Parts 1 and 2 yet, you can do so on the Science MD YouTube channel to learn more about this. Insulin resistance is not your body failing you. It's your body responding logically to an environment it was never designed for. By understanding the evolutionary roots of our metabolism, we stop blaming our willpower and start respecting our biology. And the good news is this: because insulin resistance is largely adaptive, it is also modifiable. When the environment changes, the biology follows, and that's the real leverage point. In our next video, we'll dive deeper into type 2 diabetes, including how it develops, why it's not a sudden diagnosis in many cases, what's reversible, what's not, and where medications fit into the picture. Because type 2 diabetes isn't just about high blood sugar. It's the downstream result of years of metabolic strain, and understanding that changes how you think about prevention, treatment, and long-term outcomes. If you found this dive into the science of health helpful, subscribe to the Science MD now. Let's bridge the gap between clinical knowledge and your daily life. I'm the Science MD, and this is the science behind your health. Thanks for joining, and see you next time.